You might have heard of the four-color theorem. Roughly speaking, you only need four colors for any map such that any neighboring regions are colored differently. What if we want to color a map on a torus? Can we still get away with just four colors? Turns out the answer is no, we need 7 colors. Unlike the four-color theorem, which famously requires computers to prove in 1976, this 7-color theorem on a torus does not, and was proved way earlier in 1890, which is surprising because a torus seems more complicated than a plane. In this video, let's see how this 7-color theorem can be proved. For a more systematic analysis, we reduce each region down to a point. If two regions are neighbors, like here, the red and orange regions are neighbors, then we join them by a line. In this case, these regions are so interconnected that they are neighbors with each other, but not all maps would look like this. There might be some maps out there where the neighborhood relations look like this instead. So the original problem of coloring regions can be reduced to coloring the vertices of this graph. Originally, we demanded that the neighboring regions should be colored differently. From the perspective of the graph, this means if the two vertices are connected by an edge, they should be colored differently. Graphs obtained this way will not have any edge crossings, even if the regions are very interconnected. The edges will just cross the borders between the regions. On the other hand, it can't be too disconnected. There can't be a region that literally doesn't have any neighbors. Since you can move from one region to another on the torus, you should be able to move from any vertex to any other in the graph. So we should consider graphs that have this behavior, or more simply, we consider connected graphs. Finally, we can't have more than one edge between two vertices. We only need one edge to indicate they are neighbors, but not more. After we reduced coloring regions on the torus to coloring graphs on the torus with these properties, we can finally use some results from graph theory to help us prove the 7-color theorem. Let's start with the first one, which you might have seen before. In a graph, any vertex may link to any number of vertices. We can define the degree of a vertex to be the number of neighbors it has. In this case, this red vertex is connected to 3 others, so its degree is 3. Now let's consider this slightly more complicated graph. We know that this red vertex has degree 3 because of the 3 neighbors it has. The blue vertex has degree 2 with the 2 neighbors. The yellow vertex on top has degree 2, again with 2 neighbors. And finally, the yellow vertex at the bottom has degree 1 because it only has 1 neighbor. If you sum up these degrees, 3, 2, 2, 1 adds to 8, which is exactly double the number of edges. This is not a coincidence. Every edge links 2 vertices and will be counted twice when we add up the degrees of these 2 vertices. This is a general statement for graphs, and it doesn't depend on whether you draw it on a plane or a torus. So that's the first result. E here denotes the number of edges. What about the second result? This result involves a quantity denoted as f, the number of faces, where faces are connected regions separated by the edges. We count this graph as having 2 faces, the inner pink one and the outer blue one. As long as the graph is connected and has at least 3 edges, we can say 2 things. Each edge borders at most 2 faces. It can be fewer than 2, like this edge, where both sides are the same region, but it can't be more than 2. The second thing we can say is that each face borders at least 3 edges. This pink region borders 3 edges, and the blue region even borders 4. but it can't border fewer than 3 as long as we insist that there are at least 3 edges in total. What could these little facts tell us? Let's say f1 all the way to fn are the faces of the graph, and we consider the number of edges each face borders with. We call them e1 to en. What can we say about the total of these e's? Because each face borders at least 3 edges, each of these e's here are at least 3, so the total is at least 3 times the number of faces. On the other hand, because each edge borders at most 2 faces, each edge will only appear in a count once or twice, but nothing more. So the total of these e's will be at most twice the number of edges when each edge gets at most double counted. Combining these two inequalities, we have 3f smaller than or equal to 2e, which is the second result we want. Proving the third result is actually more difficult than I originally thought, and I even dedicated an entire video to this. If you haven't watched the previous video, take this inequality on faith and come back to it later. This chi on the right is the Euler characteristic and is typically equal to 2 minus 2g, where g is the genus, roughly the number of holes. For this double torus, there are 2 holes and g equals 2. But let's leave all these aside for a moment. For any graph you care to draw on a plane, torus, and so on, we can define its chromatic number. That is, the minimum number of colors required so that no neighboring vertices share the same color. The 7-color theorem is that this number is at most 7 on the torus. Let's say that for a given graph, the chromatic number is k. Now remove vertices from the graph such that the chromatic number is still k, and stop when you can't. You end up at what I would call a minimal example for a graph with chromatic number k, in the sense that by construction, if we remove any vertex, the chromatic number is no longer k. What can we say about this minimal example? All the degrees of the vertices can't be too small. Let's assume not, so there is a vertex with degrees smaller than k minus 1. Let's assume that it is this red vertex that connects to less than or equal to k minus 2 other vertices. Because this is a minimal example, whatever we have after we remove the red vertex can be colored with k minus 1 colors. There are only at most k minus 2 vertices here that link the original red vertex. Even if they all have different colors, they only used up k minus 2 of them. So when we add back the red vertex, it can be recolored using the k minus 1th color available for the rest of the graph, which means the whole graph can actually be colored with k minus 1 colors in the first place. But we started off with a graph that requires k colors. This is a contradiction. So these minimal examples here have all their vertices degree at least k minus 1. If we now use the fact that the sum of degrees is 2e, then because individually the degrees are at least k minus 1, 2e is at least k minus 1 times the number of vertices. Just one other inequality. V has to be at least k, because if you have v vertices, you don't need more than v colors, so k is at most v. So these are all the inequalities we need, and the final steps are just massaging them. The first one we use is the Euler characteristic inequality, which we can move the e and f to the other side. Then, we use the 3f smaller than 2e inequality to deduce the right-hand side to be larger than e minus 2e over 3, which is e over 3. That's two inequalities used. Now we use the remaining pair of inequalities. The first of these gives us the right-hand side is greater than or equal to 1/6 of k minus 1v. Now that we have used this, we only have one left. But before we use this final inequality, we divide both sides of the inequality on the right by v. Now we assume that chi is less than or equal to 0, which is actually the majority of cases, because when we have at least one hole on the surface, g is positive, and 2 minus 2g is less than or equal to 0. This assumption, together with v at least k, can allow us to bound the left-hand side above by 1 minus chi over k. Pause and convince yourself that the inequality goes this way. At the end, we obtain an inequality that only involves k and chi. If we now multiply by 6k on both sides, and then put everything on the right-hand side, we get a quadratic inequality in k. Using the quadratic formula, we know that k has to be between these two roots. Again, pause to convince yourself that these are the roots. If we focus on the upper bound, there is just one small point. Because k is an integer anyway, the upper bound can be slightly tighter to be the integer part. This integer is known as the Heawood number, denoted as h of chi. So we proved that the chromatic number k has to be smaller than or equal to the Heawood number. If we are coloring on a surface with Euler characteristic chi, then as long as chi is not positive, we have an h of chi color theorem. The torus has Euler characteristic 0 because there is only one hole, so g equals 1 and 2 minus 2g equals 0. When we plug in 0 into this formula of the Heawood number, we get 7. So that's why it is the 7-color theorem on the torus. Can we use this to prove the original 4-color theorem as well? We can't, because the Euler characteristic of a plane is 2, which is positive. But let's still plug chi equals 2 into the formula and see what happens. If we plug in chi equals 2, the Heawood number is actually 4, so we do have the 4-color theorem. Of course, we can't use this to claim we have proved the 4-color theorem because our proof really relies on the fact that chi is not positive. But it's interesting that this formula technically still works. Now, how do we know that this bound is sharp? That is it possible that we can actually color the graph with even fewer colors? In the case of a torus, is it possible that 6 colors suffice? This leads us to the picture in the very beginning, or equivalently, the neighborhood relationship graph. Each vertex here is linked to all 6 other vertices, which forces us to require 7 colors. I know it's difficult to be convinced of this on screen, so you can go to the link in the description to find the GeoGebra file to play around with. Or, if you want to be even more hands-on, you can be like Weihart and color on a bagel. In any case, these show that we can't improve on the 7-color theorem, because in some cases, we do need all 7 colors. In general, there are cases where we do need all h of chi colors, not just when we have a torus. Well, the Klein bottle is the only exception to this rule, in which case we can improve by 1. The 7-color theorem was proved by Heawood back in 1890, but proving that the bound is sharp in the general case was done in 1968 by Ringel and Youngs. Their proof was very technical and involved coming up with crazy examples where you really need all h of chi colors. But this 1968 result was still 8 years earlier than the four-color theorem, showing how hard the four-color theorem really was. The summer of math exposition this year ended, but honestly I really disagree with the public ranking here, so allow me to shout out 5 entries that I like. My main criterion to judge these videos is novelty, something that I haven't heard of before. If the video features a traditional textbook argument, even if it adds a lot of visualizations and clarity, that does not count as novel to me. This might be objectively good for other people, but it's simply not my preference for a YouTube video. With that, my absolute favorite is a video on a game that features Fibonacci numbers. It was very satisfying to see Fibonacci comes out, and also, Aurora is so cute. Link in the card above and in the description below. The other 4 are mainly new ways of looking at well-known results. For example, this one explicitly and very directly demonstrates a circle in computing the integral. This video finds an elegant combinatorial proof of the identity and generalizes it much further, which is possible because the proof in this simple case was so elegant in the first place. Similarly, this video gives a good probabilistic argument for why the volume of a 4D hypersphere has this formula and generalizes it much further. The final video in the top 5 is perhaps the least visual, but its derivation of the Taylor series formula is so novel that it deserves to be one of my favorites. Again, visit the playlist of the videos mentioned because they deserve way more views. As always, thanks to the patrons and please like and subscribe. I will see you soon. Bye bye.